Welcome to Dr. Jed's continuing video series on calculus. Today's lesson is 8.4 from Rogowski, Taylor polynomials. This is sort of out of order because last lesson was 4.1, chapter 4. Now we're jumping to chapter 8. And after this we jump back to chapter 4 again. But it's related to linear approximations, which was 4.1. So that's why we're going to do it here. First thing we're going to do is we're going to start with the linearization from linear approximations to develop a quadratic. A quadraticization, I don't know how you'd say that, but an extension of the idea. Then we're going to take that extension and go farther to as many powers as we want. A third order polynomial, a fourth order, etc. And along the way we'll just mention the error bound that we had before. Well, we're going to kind of develop it for any order polynomial. And then we'll do some examples. More important than the theory behind it right now is just being able to use it. So let's talk about the linearization. Well, linear approximation, if you recall, we took f prime of a times x minus a plus f of a. Any kind of quadratic approximation should have that in it, because that was a good approximation. We just want to make it better. So the piece that goes in here, well, if you think about it, this is a constant term. This is the x minus a. That's like our x for a parabola. This would be the x squared term. And logically, this is f prime. Logically, that should be an f double prime. If you remember the error bound, that's the term we're going to use essentially. But why is it that? Why is it going to be 1/2 f double prime of a times x minus a squared? Well, the x minus a squared is there because it's got to be one more power. The second derivative is because we're going one more derivative beyond. Each derivative gives us a little bit more information about the curve. Its curvature, its acceleration, if you will, here. And the next one, the third order, will give us even more and so on. Why that half, though? Notice here, I drew the linear, and then the quadratic is set in a dashed line. Notice it is better. But let's take a simple parabola and look at it. Suppose we take y equals x squared here. We take its derivative, and then take its second derivative. Notice, the coefficient in front of x squared here was 1, but when we took the second derivative, we get a 2. We don't want a 2 in front of our thing, so we have to multiply by 1/2. That cancels out the 2 that came through this process. So what about if we do a 1 more power, a third order? Would that be 1/3? Before you decide that, let's take a look at x cubed. Take all the derivative until you get to just a number. If I'm going to get to no more powers of x, I get a 6. I don't get a 3. So for the third order, I don't want 1/3. I want 1/6. For the fourth order one, I'll skip all the interim. The fourth derivative is going to be 24. How does that come from? It comes from the 4 coming down, and then the 3 coming down, and then the 2, and well, the 1, but the 1 doesn't make a difference. But each of those numbers comes down. This is 4 times 3 times 2 times 1, which is 4 factorial. Likewise, this is 3 factorial. This is, well, 2 factorial. 2 factorial is 2 times 1, which is just 2. And if it's just 2, you don't say 2 factorial much. But each of these is the factorial because it brings each of those powers down. That may not be relevant to y, but it explains the formula, which we're going to have right here. The Taylor polynomial formula is, we have 1 over the n factorial. We need that in order to cancel out, times the nth derivative at a, times x minus a to the nth power. Then we do that for the n minus 1. The n minus 1th derivative times 1 over n minus 1 factorial. I said that in wrong order. Times x minus a to the n minus 1. And then the n minus 2 one, then minus 3 one, and so on, all the way down. So the second order term is going to be 1/2 factorial, or 1/2, times f double prime times x minus a squared, plus f prime a times x minus a, and then plus f of a. That looks messy. We'll do some examples. It'll make more sense. It's worth noting here, if a is 0, so if all of these a's are just 0, this is called a Maclaurin polynomial. Why? because Maclaurin studied it when a was 0. He studied this as things are around a equals 0. Taylor then took the idea and said, what if we go somewhere else? If a is something else, and he expanded the idea, so those are Taylor polynomials. Now the error-bound formula, if you remember, we had the error between was how far the function is from the Taylor polynomial. Well, it was linearization before. Technically it's the other order, but the absolute value is the error-bound. And just like before this was f double prime, and that was the 1/2, which was this piece. So that was because we had only these pieces. It was the one next. So if we're talking about the nth one, the next one is 1/n plus 1 factorial times the maximum that this n plus 1th derivative could ever be in between the x and the a times x minus a to the n plus 1. We're not going to worry so much about that. We'll worry more about this. So let's start with an example showing how this could work. Here's the Taylor polynomial formula again. I want to talk about the 5th order Taylor polynomial. That's a lot of derivatives for f of x equals psi. Maybe you're breathing a sigh of relief now because you go, oh, I can do those ones. In order to do this, we're going to need derivatives of 5 orders. So we need f prime of x, f double prime of x, f triple prime of x, f4 derivatives of x, and last but not least, 5 of them. And I could easily have written that parentheses 5, but I thought not to bother. So the derivative of sine is the cosine. And if you remember your derivatives well, the next one is minus sine of x. The next one would be minus cosine. The next one would be the sine of x. And the next one, the cosine of x. Now we don't actually care, if you remember the formula, we don't care what these formulas are. We care what they are at a. And a is 0. So f prime of 0, well, put a 0 in here. It's 1. F double prime of 0, put a 0 in here. Well, that one's 0. Triple, put a 0 in here. You get minus 1. The 4th one, sine. Sine is 0, which is also useful because that means f of 0 is 0. And the 5th one, well, that's the same as this first one, which is 1. Let's put it together. Some of these terms are 0. If they're 0, I'm not going to write them. But we have t5 is going to be 1/5 factorial. Times the derivative, the 5th derivative at 0. The 5th derivative at 0 is, yep, that's it, 1 x minus 0 to the 5th plus, the 4th one is actually 0, so we don't need that. Plus the 3rd one, the 3rd one has a minus 1 here. So we're going to have 1/3 factorial times minus 1 times x minus 0 cubed. The 2nd one is 0. And the 1st one is 1. So let me rewrite that. This is 1/120, by the way. And this is approximately what the sine of x is. And you may think, well, I've got a button on my calculator to do this. Well, one of the interesting things about your calculator is it uses this formula. Well, not 5, it probably goes several more iterations. It probably goes to t10 or something. Your calculator calculates sine this way. We could plug a value in. We don't need to right now. Let's do another example where we actually plug a value in. So let's estimate natural log of 1.01 over 1.01. So our function is going to be ln of x over x. And this time a can't be 0. A can't be 0 because you can't divide by 0. You can't plug a 0 in here. It just doesn't work. So our A is going to be something else. That'll be useful to talk about. And I'm only going to use T2 here because these ones are messier derivatives. I already calculated them. The first derivative is, we'll take the derivative of this, use the quotient rule. You get 1 over x times x squared minus 1 times x. You get this. Take the derivative of that, do some stuff, simplify, you get this. Now, we don't actually care what these formulas are. Remember, all we care about is plugging 1 in. And the nice thing about 1 here is the natural log of 1 is 0. So, well, first of all, plug 1 in here. 0 over 1. Plug 1 in here. 1 minus 0, so 1 over 1 squared. Plug 1 in here. That's 0, that's 1. We get minus 3. So I get T2 of x is going to be, let's do this one first. So minus 3 over, I'm sorry, let's write it the way we've been doing it. 1/2 times minus 3 times x minus 1 quantity squared plus, now let's use this one, 1 x minus 1 plus 0, and that term doesn't matter much. Let me rewrite that. Notice I don't multiply this out. This is a Taylor polynomial around a equals 1. That means all of the terms have to be x minus 1 here. Now let's plug in our 1.01 here. It's not bad. If you plug 1.01 in here, you get minus 3 halves times what's 1.01 minus 1 squared plus 1.01 minus 1. And if you do the algebra here, we get 0.01 but minus a little bit here. We get minus, so we get 0.01 minus, now this is 1.5 of those, so it's 0.00015. So I get 0.00985. There's the actual value. My calculator gave me that. Compare what we found. Notice, it's correct to 5 digits. Until next time, this is Dr. Jett.